Are you aiming for landing a business-focused data science role? If so, you should know that SQL shows up in the majority of data science job listings, according to Glassdoor. In this bootcamp-style video, I'm going to walk you through 3 key intermediate SQL concepts that not only help you crush interviews, but also solve real business problems, giving you the edge to stand out as a top data scientist. To tell the truth, SQL can be more powerful than machine learning in business context. And hey, if you stick around until the end, I'll share 1 trick of SQL, 1 interview case study from tech company, and 1 data analysis case study in business marketing. But first, here's the thing, being a top data scientist isn't just about writing machine learning code in Python. It's about answering business questions and driving real impact. In a full data science project lifecycle, it all starts with defining the problem, collecting data, analyzing it, building a model, and then deploying it into the business process. As you can see, machine learning code, like technical term and accuracy, is just one fraction part of the journey. The real value comes from using model to explain insights that support business goals, and that happens through deep data analysis. For example, in my data science role at a financial services company offering retail loans, I built a classification model to rank loan customers as easy, medium, or hard to help debt collectors prioritize high-risk cases each week, reducing credit default risk. However, the business team raised a key question: why was credit risk still high? Using SQL for deep data analysis, I found the issue wasn't the model, but the collection process. Payments were delayed and piled up until the end of the month, taking more than 10 days to receive loan payment collection. With this insight, the team shifted their strategy to speed up collections throughout the month, which definitely helped reducing credit default risk. As you can see, my data science experience above shows the power of data analysis with SQL over machine learning code because it helps business strategy execution. Mastering intermediate SQL concepts, like CTEs, joins, and window functions, covers the 80/20ths of what's needed to solve most business problems and drive real value for the organization. Before that, let's recap the basic SQL format for data manipulation. The basic SQL operations involve, first, the from clause to specify table within database, second, the where clause to filter rows based on certain variable condition, third, the group clause to aggregate variables based on common variables, fourth, the select clause to choose the right columns as output, fifth, the having clause to filter aggregated variable based on conditions, sixth, the order by clause to sort the final variable output in ascending or descending order, and seventh, the limit clause to restrict number of rows in output display. Finally, distinct clause after select statement is needed to avoid duplications in output. These basic operations serve as the building blocks for more intermediate SQL queries like common table expression, join, and windows function. We shall explore these topics one by one. A CTE, or common table expression, is a SQL command that creates temporary, reusable tables to simplify complex queries. It lets you break down operations into smaller steps, improving readability, making debugging easier, and enabling more efficient queries for advanced data analysis. Here's the standard format of a CTE. First, we start with an input table from which data can be pulled. The temporary table, or CTE_table, is defined using the with clause, where the query inside transforms the input data. Once the temporary table is created, it can be used like a regular table in the main query for further processing. But why does CTE matter? In data analysis, the traditional approach is to use subqueries. A subquery is a SQL query nested inside the main query, usually to filter or retrieve data based on conditions from another table. For example, let's say we have 2 tables, customers and orders, and we want to find customers who made orders over $100. The subquery, select customer ID from orders where order amount greater than 100, identifies those customers, and the outer query pulls their information from the customers table. While a single subquery is easy to understand, things get more complex when multiple subqueries are involved, although the basic principle still applies. Think of it like high school math. A subquery is more like a composite function, where each step depends on the result of the previous one. On the other hand, a CTE is like multiplying 2 independent functions, f of x and g of x. In other words, subqueries run in series, while CTEs run independently or in parallel. One of the key benefits of using CTEs is that they reduce complexity and minimize the risk of errors in more complex queries. If an error does occur, debugging becomes easier because CTEs break the query into smaller, manageable parts that can be isolated and tested individually. Let's revisit the previous subquery example and convert it into a CTE. We can define a temporary table, large orders, using the with syntax, which filters customers with order amounts over $100 from the orders table. The main query will then select customer information from the customers table where the customer ID matches from the large orders temporary table. If you have multiple CTEs, you can define them one after another, separated by commas, except for the last one before the main query. As you can see, using CTEs makes the main query simpler and easier to understand, especially when dealing with more complex data analysis. Next is join, a SQL command that gives you a more complete view of a customer's information by bringing together data stored across different tables. Join combines two or more tables based on a shared column, like a customer ID. There are several types of joins in SQL, including inner join, left or right join, full outer join, and anti-join, each serving a different purpose depending on the data output you need. To make it easier to understand, think back to Venn diagrams from high school math. Each circle represents a table, and the overlapping area shows the matching data, like customer IDs that exist in both tables. Visualizing SQL joins this way really helps clarify how different types of joins work by showing what data gets included, excluded, or matched. With an inner join, you're getting the intersection between two tables, only the records that match in both. For example, if you have a customers table and an orders table, and you want to list orders along with customer names, an inner join will only return customers who have actually placed orders. Let's say customer IDs 1 and 2, John Doe and Jane Smith, have placed orders. The result will only include them. And if you look closely, you'll see John Doe appears twice. That's because he made two purchases, a laptop and a keyboard, so his customer ID shows up twice in the orders table. Now let's flip it and talk about a full outer join. You can think of it like the union of two tables. This join includes all rows from both tables, and fills in nulls where there is no match. This is useful for answering business questions like, which customers have placed orders, and which haven't. For example, if we have a customers table and an orders table, a full outer join will give us the full picture, all customers, all orders, and how they do or don't relate. In the result, if a customer like Bob, customer ID 2, hasn't placed an order, you will see nulls in the order columns. On the flip side, if there's an order like tablet that doesn't match any customer, maybe due to missing or deleted customer data, you'll see nulls in the customer columns. A left join returns all the records from the left table, or table 1, and pulls in matching data from the right table, table 2, based on a shared column, like a customer or student ID. If there's no match, the right table's columns will just show null. The key thing to remember is, the number of rows in the result will always match the left table. Every row from the left table is included, whether or not there's a match in the right table. For example, if we have a students table and a departments table, and we left join them, we'll get all students listed. But if a student, like those with IDs 1001, 1002, and 1003, isn't assigned to any department, you'll see null in the department column. A left anti-join returns only the rows from the left table that don't have a match in the right table. You can achieve this by using a left join and then adding a where clause to filter for null values in the right table's key column. For example, say you're trying to answer the business question, which customers haven't made any purchases? You'd left join the customers table with the orders table, then filter where customer ID is null from order table. This gives you a list of customers who never placed an order. A right join works just like a left join, but with the reference table on the right side instead of the left. The concept is the same, just flipped. When deciding between a left and right join, it's all about identifying which table is the reference table and the direction of the join. In practice, though, if we're clear on the reference table and the join direction, that is using the left join, we usually don't need to use a right join. In the first bonus chapter, here are some best practices when writing SQL queries with joins. First, use table aliases. Always assign aliases to tables. This makes it clear which columns belong to which table, especially when there are columns with the same name in different tables. Aliases improve readability and make complex queries easier to maintain. Second, use distinct. When selecting columns after a join, add the distinct keyword right after select. Joins can sometimes produce duplicate rows, and distinct ensures that only unique rows are returned. Third, perform due diligence. Always double-check that 1 + 1 = 2. Make sure the number of unique customer IDs remains consistent before and after the join. If there's a mismatch, it could mean something went wrong with the join, leading to row duplication. This helps us explain any inconsistencies if they come up. Finally, draw a Venn diagram. Before you start joining, visualize the relationship between tables using a Venn diagram. This makes it easier to choose the right type of join for your data. In this third chapter, here comes the most exciting part of this video, that is a window function.
A window function in SQL performs calculations across a set of rows in a table without requiring a grouping clause. In other words, window functions allow users to retain individual rows even if there are duplicates customer, while still performing calculations on the data. A business application of window functions could involve calculating cumulative metrics, such as total spending over time for an individual customer with multiple transactions on different dates. Another use case could be determining the average number of attempts needed to convert customers in a marketing campaign. The basic syntax for window functions in SQL follows a specific structure and logic. First, we start with the window function. This is the aggregation function or calculation we are trying to perform, like sum, average, maximum, and minimum. Second, we use the over clause. This is where we define the reference point for the function to start, based on partition and ordering. Third, there's the optional clause in partition. If used, the result set is applicable into groups of rows based on particular column, and the window function is applied to each group separately. Fourth, we have the order clause, which is also optional. If we choose to include it, it specifies the sequential order in which the rows should be processed within each partition. Without order by clause, there won't be any sequential order for the windows function to execute. In this first example, the window function will calculate the cumulative salary using the sum function and the partition clause on department ID. The order clause ensures that the cumulative calculation occurs in sequential order, based on salary that is from lowest to highest. For instance, in department ID 10, the sorted salaries are 50K, 55K, and 60K. As a result, the cumulative salary in that department would be 50K for the first row, 105K for the second row, and 165K for the third row. If we want the salaries sorted from highest to lowest, we can simply add desk statement after salary statement in this window function. The same logic applies to other departments, such as department ID 20. In this second example, the window function will calculate the total salary for each department using the partition clause on department ID, but without the order clause, meaning there is no sequential order. As a result, the total salary for each department is the same for every employee within that department. For example, in department ID 1, the total salary would be 165K. In department ID 2, it would be 180K, while in department ID 3, it would again be 165K. Other than aggregation, I will share ranking window functions like rank, dense rank, row number, and n-tile, which are useful for analyzing sequential patterns over time. The rank function assigns a rank to each row based on the order clause applied to the salary column. If two or more rows have the same value, such as the 75K salary appearing twice in this example, both rows will receive the same rank, that is rank 2. However, the next rank, or rank 3, is skipped after these equal values. This is why we see rank 4 following rank 2. The dense rank function works similarly to the rank function, but it doesn't skip rank numbers when rows have the same values, such as a salary of 75K. As a result, in this example, we see rank 3 immediately after rank 2, without any gaps. On the other hand, the row number function assigns a unique number to each row in sequential order, even if there are ties in the data. Therefore, every row gets a different rank number, even when the values are the same. The n-tile function divides the rows in a table into an equal-sized groups, also called tiles. In this example, using n-tile of 4 divides the table of 8 employees into 4 equal-size groups. For example, the first tile, or tile 1, contains the top 2 highest salaries. The second tile, or tile 2, contains the next 2 highest salaries, and so on. If the number of rows isn't perfectly divisible by the number of tiles, for example n tile of 3 from 7 records table, the nTile function will try to distribute the rows as evenly as possible, like in this example. The first tile has 3 records, while the second and third tiles have 2 records each. Another type of window function that incorporates the time element to see comparison analysis across different time period is the lead and lag window functions.
In this example, the lag function is used to retrieve the prior visit _date within the same customer ID partition. For example, for customer ID 101, it indicates that 9 days have passed since the last visit on March 1, 2025. The previous _visit column shows null for the first visit of each customer, such as for customer ID 102 on February 15, 2025, because there is no prior visit to that reference date. In marketing retention, lag helps compare a customer's current transaction or interaction with their previous one, or backward approach. Lead works similarly to lag window function, but lead retrieves the next subscription _date within the same customer ID partition. For example, for customer ID 101, it takes 1 month for this customer to renew the subscription after February 10, 2025. The next renewal date shows null for the last subscription date for each customers, such as for customer ID 102 on March 15, 2025, because there is no subsequent subscription to that reference date. The choice of using lead and lag window functions depends on the reference direction, whether you need to look forward versus backward within a partition.
In this second bonus chapter, let's dive into real SQL data science interview from Amazon.com, where the problem statement asks about calculating top highest grossing items. Assume we are given an input table containing data on Amazon customers and their spending on products in different category. Write a query to identify the top 2 highest grossing products within each category in the year 2022. The output should include the category, product, and total spend. To answer this question, we must grasp the hints such as top 2 highest grossing products for each category and for any transaction in the year 2022. Now, let's take a deeper look for the output table. Each row in the output will represent a unique combination of category and product, such as appliance refrigerators or electronics vacuum. A single category, like appliance, can appear multiple times with different products, but for each category, we want to display only the top 2 products based on total spend. Therefore, this can be achieved by using a combination of window functions and grouping. Let's write the SQL syntax based on the concepts we have discussed previously. First, we'll begin by filtering the product spend table to include only transactions that occurred in the year 2022. To get total spending amount of each unique pair of category and product, we can group on category and product, and write some function of spend column on select statement after category and product, to compute total spending. Second, to identify products ranking within each category, we'll use a window function like rank or dense_rank. This will allow us to assign a rank number to each product, based on the total spend amount. The ranking should be based on each category, and it will be sorted by the total spend amount in descending order, from highest to lowest. Finally, to get the top 2 products, we can simply filter the ranking to be less than or equal to 2. To keep the query simple and avoid using complex subqueries, let's use a common table expression, or CTE. We can define the reference temporary table, named ranked_spending_table, using the with clause. After that, we can simply perform simple query on this temporary table by selecting category, product, and total spend where ranking is less than or equal to 2. Before continuing to next SQL topic, if you like this video content, please consider subscribing my channel so that you won't miss for my future videos about tips on how to succeed in data science for business world. Feel free to drop comment below and I'd be happy to answer. Okay, let's continue.
Now, let's use online retail dataset from Kaggle.com to get hands-on practice, with link in the video description below. First, let's start with data cleansing. The online retail dataset contains around 542,000 transactions from various countries from the year 2010 to 2011. To ensure consistency in currency, I filtered the data to include transactions only in UK with valid customer IDs and quantity greater than 0, resulting in approximately 354,000 clean records. Next, using Python code, I removed the time component from the invoice date and converted customer IDs into string format for easier analysis. Second, before diving in, we must define a clear business objective, that is measuring how frequently customers make purchases to allow working backwards. Technically, this objective can be measured by calculating the average number of days between purchases using SQL window functions in lead and lag. Consequently, customers with shorter interval durations can be considered as frequent buyers. Third, we use subquery, or inner query, inside main query. Inside the inner query, the window functions lead and lag work to look at previous and next invoice date for all transactions for every customer ID, using the partition clause, sorted from earliest to latest invoice date, using order clause. In the main query, we use the julianday function to convert the dates into numeric values to perform calculation on dates. Then, by subtracting the invoice date from the next invoice date, we calculate days until next purchase. Similarly, subtracting the previous invoice date from the invoice date generates DaysSinceLastPurchase. From this script, we can see that SQL window functions work by retaining individual transaction records for each customer without aggregating or grouping by customer ID, enabling detailed transaction-level analysis. Let's store the output table from this window functions into a table so-called retail data second version. Finally, from retail data second version as generated previously, it is time to aggregate the data at customer level by grouping customer ID to generate summary statistics for each customer. The query calculates the following metrics such as total quantity purchased, average item purchase price, average days since last purchase, and average days until next purchase. Additionally, a case statement is used to segment customers into two categories, frequent buyer and not frequent buyer. This can be from average days until the next purchase, or average days since the last purchase. Customers with an average of 7 days or fewer between purchases are labeled as frequent buyers, otherwise, they are classified as not frequent buyers. In the final result, as obtained through pivoting summary in Excel, we observe that frequent buyers have an average item price of £3.3, which is lower than the average for non-frequent buyers of £4.1. This insight suggests that frequent buyers tend to purchase items at lower price. Based on this, the business could consider offering discounts on higher-priced items to encourage non-frequent buyers to make more purchases, ultimately increasing both transaction frequency and revenue.
Now, with the SQL concepts in this video, you can practice and be more confident to pass the SQL data science interview. But passing the interview is just the beginning. Click here on this next video to learn some common mistakes data scientists make and tips on how to avoid them for long-term career success. Thanks for watching.